Okay, so we have relations. That's another way to get functions. Now, you could probably guess, since relations are ordered pairs. Let me see my recording. Since relations are just collections of ordered pairs, you can probably see that, or at least predict, that there will be a connection with graphing. There will be some kind of connection with graphing. But before we get to the graphing connection, I want to point out some notation, which is also very important. Here, usually for a function, what we like to do is we like to use letters, well, as you saw already, F. Sometimes people use G, H, or capital letters like capital F, capital G, capital H. Usually from the context, you'll be able to tell what notation is being used for the function. You will be able to tell. And usually it's going to be letters like F and G. Just like we use little x usually as a variable for numbers. Usually people use F and G for functions. I mean, I'm guessing that's just, what do you call it, convention or whatever, or tradition, I don't know. But that's just what people do. And this was in the definition as well. The little x here, that's usually going to denote an arbitrary element from the domain. X will usually denote an arbitrary element from the domain. Now, x goes into the function, but what actually comes out is going to be denoted by this. And this is actually read as f of x. F of x, not f times x. It's f of x. So again, this is just notation. F is our function. X denotes an arbitrary input from the domain, or an arbitrary element from the domain, and the actual output you get is f of x here. F of x. And not only that, people also write this. This is actually notation for the above statement, the above definition, that is. Because remember how y represents an arbitrary element in capital Y? And what we're saying is the function f gives us the element in set y. The element it gives us is f of x. In other words, when you see this notation, essentially you have all this floating in the background. That's really what we're saying. Again, it's just notation people use. The little y, remember, represents an arbitrary element in the set capital Y. But what we're saying here is that the element we get back is denoted also by f of x. And we say also y is a function of x. That's what we also like to say. And this is also, again, there's a lot of terminology here. I understand that, but math does have vocabulary, just like other sciences do. X is also called the independent variable. This x over here. And y is actually a variable as well, because x is, if you change x here, you're going to change y generally. So y is also called a dependent variable, as you can see. So we say that x is the independent variable. Y is the dependent variable. And y equals f of x. Okay. Again, this just means f is a function from capital X to capital Y. Okay. You have this definition floating in the background. That's all we're saying. And this is something else, actually. With those ordered pairs, right? We saw relations where you can have a function. If you do have a function, right, we actually can think of each ordered pair like this. We can actually think of each ordered pair like this. So the y coordinate, right, is actually f of the first coordinate. I'm guessing that was the inspiration for this notation altogether. You know, the y coordinate, right, the variable for the how do you say, the elements in a range, well, the elements in set y, that's what little y is, right? And we're saying that f is the function from x to y. It's just another way of visualizing it. I mean, I hope all this helps. I know I'm kind of like repeating myself a lot. Again, this is not easy stuff. My experience is that students have a lot of trouble with this. So that's what we have here. So that's what we have here then. Okay, so for each ordered pair, I mean, we didn't say the function was f or g, but the input, the x coordinate goes in, and you get the y coordinate back. The y coordinate is really f of the x coordinate. Okay. Okay, so that's good. All right. Now, as I said before, I know we really need to do more examples of this. So I'm guessing, I mean, I'm not going to stop. I'm not done yet. I'm guessing on Friday we'll do more examples. Let me say this as well. Any relation, right, is a collection of ordered pairs. We have seen before, okay? We have seen before that a graph in the Cartesian plane, I think we saw this at the beginning of chapter 2, a graph in the Cartesian plane, okay? It's nothing more than just a collection of points plotted in the plane. That's all it is. It's just a collection of points, you know, that you plot in the plane. So from any relation, we can get a graph. And theoretically, from any graph, we can get a relation. Although that relation might have many elements to list. So that should indicate to you that, oh, well, certain relations can give us functions, right? So certain graphs can give us functions. So there is that connection. You have to be careful because just like there are relations that are not functions, there are graphs that are not functions. And that's where this vertical line test comes into play. Basically, the vertical line test is a way to determine if a graph you draw in the plane is the graph of a function. Okay, so again, a relation can give us a function. Relations give us graphs, and from graphs we can get relations. So in other words, graph is another way to define a function. And how do you know if you have a function from a graph? You know, like those, just like for relations, we had to see, well, does this happen? Does that happen? Some kind of test? Well, we have this vertical line test for a graph. Basically, what this is saying is if you can draw a vertical line, a given graph is the graph of a function, if every vertical line intersects the graph at most once. Is that word missing from there? Oh, sorry. Exactly when, yeah, something was blocked by this little symbol, by this symbol here. So basically, again, it's a graph exactly when no vertical line can intersect the graph more than once. In other words, any vertical line you draw in the plane is going to intersect that graph at most one time. Either it won't intersect it or it'll intersect it only once. What's nice is if it does pass the vertical line test, we can think of every point in the plane, in the graph that is, of this form. Like so. just like remember, if a relation is a function, you could think of every ordered pair in that relation as looking like this. Take graphs. What's nice is a non-vertical line is in fact the graph of a function. I mean, it should be easy to see that, this line that's not vertical will easily pass the vertical line test. Let me see if I can draw it actually. No, wrong thing. I want the pen. There we go. Now, if I draw, oh my goodness, use your imagination. That's a vertical line. But you can hopefully see that any vertical line I draw is only going to cut through that graph at most one time. Okay? At most one time. Circles, however, that's a different story. Yes, there are vertical lines like this one that won't intersect the graph. But watch this. Uh-oh. This fails the vertical line test. Right? You have a vertical line here that intersects the graph more than once. Right? So unfortunately, the circle here does fail the vertical line test. Okay, we have less than a minute left. But there's definitely more to this section. I mean, the notes, there's not much more. I didn't think I would get this far. So what I'm thinking now is maybe next time we'll do some kind of worksheet, just for practice, because I really want to do examples, because I know this is not easy. But let me just say this, though. Again, from relations, you can get a graph, right? And so we can determine if we have a function or not. And then we'll see later on that from equations in x and y, you can get functions. Namely, you have a function if the graph passes the vertical line. I mean, there's more to it, but for this class, I think that would be good. So anyway, let's stop now, okay? All right.